All right, so let's consider this problem where we have a wheel and axle and we're pulling up this box, 45 kilogram box into the air at a constant velocity. The height of 1.25 meters and the time we'll say is 3 seconds as we lift it. So go ahead and calculate the work done in lifting this as well as the power output, and when you're ready you can continue the clip. So go ahead and hit pause, and then when you're ready you can continue. Okay, so we have our force supply going up, force of gravity going down, going at a constant velocity. So no forces in the x, but in the y, positive force applied plus the negative force of gravity equals 0. We add them up, so the force applied is equal to the force of gravity. We get 441 newtons is the force applied going up. And to find work, we take that value, multiply it by 1.25 as the displacement. The force applied is up, the displacement is up, so the angle between those is 0. 551.25 joules is the work done, and the power, taking the work divided by time, is 183.75 watts. Okay, so let's go ahead and apply this to a situation where we have this record-setting feat by the person climbing these stairs, running up 1,600 steps of the Empire State Building in 10 minutes and 59 seconds. If the height gain of each step is 0.2 meters and the man's mass is 70 kilograms, what is the average power output during the climb? So let's go ahead and do this in watts and horsepower. If we consider the forces here, we'll consider the force of going against gravity, right? So any horizontal movement does not count as work. Only what is parallel to the force applied. And so the only work that counts is what's vertical. So we have the force applied going up, force of gravity going down. We have the displacement that you can solve for. So go ahead and pause the clip and see if you can calculate what the power output is in watts, and then I'll give you the conversion when you're ready for that. But go ahead and calculate the work done and then the power, and then see how you do. So go ahead and pause the clip and then you can continue when you're ready. Okay, so we should have, if we look at the force applied, 686 newtons equal to the person's weight, and we multiply the number of steps by the height of one step. So the total amount of work that was done is 219,520 joules. And we can divide that by the time, which 10 minutes and 59 seconds is 659 seconds. And the power output here is 333.11 watts. The conversion to horsepower is 7.46 watts. So 0.45 horsepower is the value that we get here. All right, so let's go ahead and consider this situation with a bullet that goes into and through a tree, okay? So let's say that the bullet passes through the block, diameter of 37 centimeters that it passes through, and let's say the initial speed of the bullet is 275 meters per second, and after it goes through, it's slowed down to 110 meters per second. Say there's a negligible drop in height. Go ahead and find the non-conservative force in this case. So you could ignore the small change in gravitational potential energy change. So let's, as we set this up, you can consider there's no change in gravitational, although there would be a little bit in reality, but we'll assume it's negligible here as it goes. There's no springs involved, right? So you're dealing again with kinetic energy and non-conservative work. So go ahead and pause the clip and calculate the non-conservative force of friction bringing this bullet to a stop. Okay, so we know that the force would be negative here. We have the displacement, which is the 0.37 meters. We're looking for how much force there is that it changed, and we do have a final speed and an initial speed. It doesn't come to a stop. When we place our numbers in there, we should end up getting a non-conservative force of 25,753.38 newtons. So that is the non-conservative work bringing this to a stop. All right, so let's go ahead and consider this one here. What is the speed of the pendulum bob at point B if it's released from point A? This is a challenging question because you have to really kind of use what's given here and use some geometry to figure out what's going on. So do your best. Go ahead and pause the clip, and we'll assume no friction here, no non-conservative work. So complete energy transfer, no springs involved. So kinetic and potential. So see if you can, calculate, what the speed will be at the bottom, and when you're ready, you can continue. Okay, so the key here that you would have to do is set up a right triangle. We have the angle here is 40 degrees. We want the adjacent side here so that, once we have this value, the, 1.149, we know if we subtract from, this 1.5 is 1.5 here, so we can figure out how high this is, and that is 0.351. So that is actually the initial height. So when we place that in here, this is the initial height is the 0.351 here, and then the final height is 0 at the bottom. The final speed at the bottom is what we want, and it's starting from rest. It's released from rest, so the initial speed is 0. And mass will cancel from both sides, so we'll get a speed of 2.623 meters per second at the bottom here. Okay, so this will be the final question in this unit that we'll try. What is the power output of a 1 gram fly as it walks straight up a window pane at 2.5 centimeters per second? So yeah, go ahead and set up some of the forces, or the free body diagram, some of the forces, and you can go ahead and try to determine the power output. Again, this one may be helpful to look back at your power equations. There's 2 ways to calculate power, so you can evaluate that. So go ahead and try that, and then when you're ready, you can continue. Okay, so you have the force applied going up, the force of gravity going down. You should have the force of gravity, as equal to the force applied. 0.0098 newtons is the force applied going up. For the work, you could have solved for, you've got the force going up, you've got the displacement going up. The cosine of 0. So this is how many joules of work it is going up, and we have the certain amount of time. Now the other way to do this would be to take power equals force times velocity. We know the speed in centimeters per second, which we can convert to meters per second. We have the force, which is this force here, and you'll end up getting the same value.